Okay, so we're recording, I think, which means let's go ahead and start since we haven't had anybody trickle in the last minute or so. Shahar maybe will join in a bit, maybe he won't, I guess we'll see. The goal today is to finish up at least section 7 on random walk expanders. Maybe we'll start seeing a little bit of the sampling applications. I'm not sure if we're going to get to that or not. Regardless, Shahar will either start or continue sampling applications on Thursday. So we'll get to see some kind of surprisingly direct applications of the material we're going to cover today. It's not kind of immediately obvious that the techniques we're going to talk about today actually have applications in mixing, but just kind of we'll see that very slight adjustments of what we do today will have kind of huge effects in applications on sampling and MCMC algorithms. And we'll talk about what these are more later. Okay. So I want to start by briefly reviewing a few things from last time. So what did we talk about last time? Well, we formally defined the higher order random walks, right? The upper, lower, and non-lazy upper walks. We use this to define random walk expansion, the extension of, so remember on graphs, we showed a couple lectures ago that this idea of random walk expansion was an exactly equivalent way to talk about spectral expansion, two-sided spectral expansion on graphs. And we showed how to generalize this definition last lecture to simplicial complexes. We didn't show yet kind of why it was a natural extension. But we at least defined the kind of some generalization of random walk expansion to simplicial complexes. We talked a little bit about one way to think about this, where kind of you think about the up and down operators as commuting. Today we're going to talk about a different way to think about it, which is in fact to prove that random walk expansion, which is a global property, is somewhat surprisingly basically equivalent to local spectral expansion, which is mostly a local property. So that'll be the main thing that we're trying to prove today. And I think we should be able to get through the proof, but let me write some kind of reminder definitions that we'll be using today, just to make sure everybody's still on the same page. So I want to start with reminding you what the upper and lower walks are. So upper and lower walks. So this is just, given a d-dimensional complex, let's say x pi, for all k less than or equal to d minus 1, the upper walk at level k. So you can't have an upper walk at level d, right? Because you can't walk up past the highest level of the complex. So it only goes from from 0 to d minus 1. We have an upper walk. So the upper walk at level k is just the composition of the averaging operators. It's dk plus 1 uk. And remember that in diagram form, so it's almost always easier to think about these things in terms of the Hasse diagram form, even though formally you want to think about them in terms of these averaging operators. But remember, all that this is doing is it starts at level k in the diagram, it walks up to level k plus 1 in some kind of conditional way upon the distribution pi, and then it walks down back to level k uniformly at random. Right, so this is the upper walk. And we talked about exactly what kind of this conditional movement up and down were. It's formalized by the averaging operators, but it's useful to just think about it as kind of taking a step up and a step down in the complex, somehow conditional on the distribution pi. So then we have the lower walk, which is for all k greater than or equal to 1. So again, you can't have the lower walk on level 0 because it walks a step down and a step up, and there's no step below 0. So the lower walk is only defined from 1 to d. So the lower walk at level k is what? It is dk on the right-hand side, uk minus 1. And if we draw our diagram again, like I was saying, this is the walk where we start at level k, and then we walk down to level k minus 1. and then back up to level k, right? Again, now down is still uniform, and up is this kind of weirder conditional distribution based on pi that we talked about last time. And these are both, operators mapping ck to ck, so operators in the space of functions on xk to xk. So kind of on the right-hand side, you can think about them as averaging operators. On the left-hand side, they correspond to these random walks that I'm talking about. We'll usually think about them kind of as the, well, it's useful to take different views. Sometimes we want to think about them as kind of the averaging versions. Sometimes it's useful to think about them as the random walks. So both views are useful. And then I want to recall that we proved last time that the upper walk has a lazy component, right? So recall that dk plus 1 uk has a lazy component of 1 over k plus 1, right? So in particular, we proved that the probability, so if you start at, say, a face sigma, and then you walk up to sigma union v, the probability of returning to sigma is always 1 over k plus 1. And why is this the case? Well, we actually proved it by like going formally through the transition probabilities and showing that it was 1 over k plus 1. But even informally, this is really easy to see, right? Because when you walk down by removing a vertex uniformly at random. So the only way, whenever you walk up in the complex from sigma, you walk to sigma union v. So the k plus 1 face that you walk to will always still contain sigma. So what's the chance that you end up at sigma after removing a vertex? Well, you have to remove v, right? If you remove something in sigma, you won't end up back at sigma. So it's exactly the probability that you remove v. And since you remove a vertex uniformly at random, and there are k plus 1 vertices, the chance of removing v is 1 over k plus 1, right? So this is exactly the same as when we did the node edge node walk, right? When we walked up to the edge, that edge always contained the starting node. And then there was a 1/2 chance of returning back to that node. So now instead of 1/2, it's 1 over k plus 1. Right? So this is kind of the generalization of what we saw on the node edge node random walk. And this motivated the following definition, right? When we defined random walk expansion on graphs, we defined it with respect to the adjacency matrix, not with respect to the node edge node walk. And we want to do the same thing here. Hi, Shahar. We want to do the same thing here. We want to define it with respect to the non-lazy upper walk instead of the upper walk that has this lazy component of 1 over k plus 1. So this motivated the definition of the non-lazy upper walk. So let's remember what that is. Non-lazy upper walk. And this was equal to basically, although Shahar liked writing it the other way, but this is basically just the upper walk minus the lazy component, and then you renormalize it to make sure it's still stochastic, right? So this is the upper walk, dk plus 1 uk, minus its lazy component. So the lazy component is the diagonal, and every one of them is 1 over k plus 1, right? So this is just the identity times 1 over k plus 1. So you subtract off the lazy component, and then to make sure it's still stochastic, you renormalize. And last time we worked through exactly what are the transition probabilities of mk plus. And recall basically what we learned was that kind of mk plus, the probability of moving from, I think we denoted it as tau to t, was what? Well, it was, I think we said 1 over k pi k plus 1 tau union t over pi k plus 1 x tau. Basically, if tau and t were neighbors, if they were only 1 away, if their intersection size was equal to k minus 1, and otherwise we saw it was 0, right? If they were equal, there's no lazy component, so if they were equal, it was 0. And we saw that it's fairly clear that if they're more than 1 away, because you only walk 1 step up and down, you can't possibly get to something that's more than 1 away. So it's kind of 0 everywhere else. And then there's this version that kind of looked like the adjacency matrix for kind of neighboring k faces. So we'll actually use this form later today when we prove the equivalence of local spectral and random walk expansion. So I wanted to remind you of it. Okay, so finally, we then use this to define random walk expansion. So how do we define random walk expansion? So we call x pi a gamma random walk expander. And let's say this is a d-dimensional complex still. If for all k between, strictly between 0 and d, basically because we're going to need both the upper walk and the lower walk to be defined at these levels. So you have to take out 0 and d. The non-lazy upper walk is similar to the lower walk spectrally, right? If mk plus minus the lower walk, uk minus 1 dk, has spectral norm less than or equal to gamma. So its largest eigenvalue in absolute value is bounded by gamma. So this was the definition that we ended up with. And for k equals 1, what was the specification here? Well, remember that m1 plus is just equal to the adjacency matrix, right? If we plug in kind of k equals 1 here, what we get is exactly the way to how we define the weighted adjacency matrix of a graph. So for k equals 1, this reduces to, and the lower walk at level 1, right, as you walk down to the empty set and then kind of uniformly up to everything. So this just reduces to, I guess, on a regular graph that we discussed, this was exactly the definition on graphs. So this was indeed kind of a direct generalization of the notion of random walk expansion that we defined on graphs. So now instead of just at k equals 1, we want this equivalence between the non-lazy upper walk and the lower walk to hold, or this kind of approximate equivalence, to hold for every level between 0 and the top level of the complex. Okay, so that's all I'm going to review. Basically the rest of the lecture. So we're going to see an example of a random walk expander next. I think I mentioned this at the end of the last lecture. We're going to look at the complete complex. And then we're actually going to show an equivalence between local spectral expansion and random walk expansion. But before jumping into that, I want to pause to ask, are there any questions from last time or from this overview about the upper and lower walks, about our definition of random walk expansion? Any questions before we kind of dive into a slightly more technical example of proving something is a random walk expander? Okay. If not, then let's go ahead and go into our example. So, I mean, I think I mentioned this last time, but throughout this course, every time after we've defined a version of expansion, whether it's on graphs or on special complexes, the first thing we've always looked at is we've always wanted to check, is the complete object, basically a perfect example of this. And this is because kind of morally, our definitions of expansion are supposed to have kind of something to do with robust connectivity of your object. And the most robustly connected, the most possible robustly connected object is always the one that has, all edges, that has everything, the complete object. And so, this is just kind of a double checking. Is this even, is there a hope that this is a reasonable definition of high dimensional expansion? It better be satisfied by the complete complex. The complete complex better be essentially an almost perfect random walk expander. And we'll see indeed that it is. So our example will be JND, which is the complete complex on n vertices in d dimensions. So this is the complex given by the dth level is just all d size subsets of n, and you take the uniform distribution. So pi d is uniform. So this is the complete complex. We've seen it before. We proved already that this was a local spectral expander. Now we're going to show it's a random walk expander. Okay, so what do we need to prove? So in general, our goal is to bound kind of for all k between 0 and d, our goal is to bound the spectral norm of mk plus minus the lower walk minus uk minus 1 dk. And so far in this course, whenever we wanted to bound a spectral norm or like the second eigenvalue or the last eigenvalue, we've basically always done the same thing. We've taken a look at the Rayleigh quotient and we've tried to bound the Rayleigh quotient. And we actually, later in the lecture, we will in fact do this. We'll look at bounding the Rayleigh quotient of MK plus minus the lower walk. But this time we're actually going to do something a little bit simpler. I'm going to show you a kind of a weaker way to bound the spectral norm. And I'll tell you about that in just a second, but it'll actually be useful first to take a look at kind of what the values of MK plus minus the lower walk actually are, right? So I guess let's think about this in terms of the standard basis, or you can think about this as kind of the difference in transition probabilities between MK plus and the lower walk. I just kind of want to write out first explicitly what are the values here. So in particular, let's compute for all tau prime and xk. Let's compute MK plus minus UK minus 1 dk of tau prime. Kind of the difference in transition probabilities from tau to tau prime between the non-lazy upper walk and the lower walk. Okay, so I claim the following, which I'm going to leave as an exercise, and I'll mention why it's a good exercise in a second, that this is the following form. There are three cases, unsurprisingly, right, based on the intersection size of tau and tau prime. We've already seen how this intersection size kind of controls what MK plus looks like. It's the same for the lower walk. So in particular, so one of the cases is tau is equal to tau prime, right? They're kind of as close as possible. They're equal. And in this case, well, we already saw that MK plus was 0, right? Because MK plus is non-lazy. And the lower walk, I claim, has, in this case, looks like 1 over n minus k plus 1. The second case is when tau and tau prime are essentially neighboring, right? They only differ by 1. And here it's slightly more complicated. This will be 1 over k times n minus k times n minus k plus 1. And then this last one should be fairly obvious, right? In every other case, just like before, when tau prime and tau are more than 2 apart, both of these walks only take a single step, right? So they can never get to anything more than 1 apart. And so both of the transition probabilities are 0. And so this final one is 0. Okay, so kind of overall, I'm going to leave the proof as an exercise. But let me take a moment to say why I think this is a useful exercise. So you could go through this by kind of writing out all of the definitions of the up operator and the down operator and MK plus. And you could go in and look at all the probabilities and compute everything. And this would certainly be a valid way of doing it, of doing the problem. But because we're on the complete complex and our distribution is uniform, you can basically get away with instead kind of just intuitively working with the random walks. Essentially, because our distribution is uniform, when we look at the upper and lower walks, when the upper walk walks uniformly at random up and uniformly at random down. So it's a very simple process. The lower walk is similar. It walks uniformly at random down a step and uniformly at random up a step. And so instead of kind of working through all the definitions of U and D, this is a good example of when you can kind of just go in and say, well, okay, what does this walk? It walks up 1 step uniformly at random and then down 1 step uniformly at random. And you can just kind of look, combinatorially at kind of, for instance, this walk should maybe spread out evenly across certain types of faces because everything is symmetric and everything is uniform. And so you can use kind of this fact that you're on the nicest possible complex to just use it, get an intuitive understanding of the lower and upper walks and use it to compute these values. So I claim that kind of you can prove this without going through all of kind of the technical details, just by knowing that the walks are kind of a uniformly random step up and a uniformly random step down, and that the complex is completely symmetric. And I think that doing it with the way where you write out the up and down operators, et cetera, is maybe useful for working through the definitions of the up and down operators. But I think that proving this kind of just looking in terms of only the random walk view is very useful for getting a moral intuition for what these random walks look like. So I'm going to leave it as an exercise. Maybe it's worth actually doing both ways. To think about why you get these values when you just think about the walk as this symmetric walk that walks uniformly at random up, uniformly at random down, or at random down and then up for the lower walk. Anyway, I think this is a useful exercise and not too difficult. Okay, so why have I done this? Why am I writing out the transition probabilities? Well, it's going to be useful for this kind of weaker way of bounding the spectral norm that I am about to tell you about. In particular, instead of bounding the Rayleigh quotient, what we're going to do is we're going to basically bound a different matrix norm and then prove that this actually bounds the spectral norm instead. So in particular, what we're going to look at is bounding the maximum L1 norm of the rows of this matrix. So let's, for simplicity, let's call this E as like an error term. This will actually hold for any operator, not just for mk plus minus uk minus 1 dk. But so let me make this claim about kind of a new way to bound the spectral norm that we haven't seen so far in this class. And in particular, I claim that if, just what I said, if the maximum L1 norm over rows of E, so EI, I'm just saying, is the ith row of E. So is ith row of the matrix E. If this is less than or equal to delta, then I claim that the spectral norm is also bounded by delta. So it should now be immediately obvious, why it's useful to look at these values and why the fact that they're so small is probably going to imply a bound on the spectral norm, right? I'll prove this claim for you, but just note that, these values are about 1 over n or 1 over n squared. And if there kind of aren't too many examples of tau and tau prime that are neighboring, if we can sum up their, if we can look at the L1 norm of a row and it's small because all the values are small, then we can get a pretty good bound on the spectral norm. And we'll see that, I'll show this explicitly after I prove the claim. But just some, intuition of why I wrote out these transition probabilities. Using this claim, we're going to be able to just directly use them to easily compute a bound on the spectral norm. Sorry, 1 second. Okay, so let's prove this claim. Oh, actually, I want to make one more note about this claim, which is that you don't, we're in particular going to use this L1 norm of rows, maximum over L1 norm of rows. But actually, this is true, I believe, if you trade out this statement with any matrix norm. So it turns out that kind of the spectral norm is, in a sense, like the weakest norm. You end up getting, sorry, 1 second. Keep getting computer notifications. Okay, you can basically, if you plug in any spectral norm on the left and it's bounded by delta, it implies an upper bound on the spectral norm. The L1 norm of the rows. Sorry, Shahar, did you have it?
Oh, go ahead then.
The L1 norm of the rows tends to be a particularly easy matrix norm to compute. As we'll see here, it's also used kind of in actually the high dimensional expansion or kind of application literature and the sampling literature. They often use this type of bound, not necessarily to prove random walk expansion, but to prove related notions of high dimensional expansion. So this is a useful tool to have in your toolkit. It's a nice way to bound spectral expansion without having to kind of go through the Rayleigh quotient if things are maybe too complicated to use the Rayleigh quotient.
Yeah, maybe I'll just say one thing. So you said that you can replace it with any matrix norm. I mean, this requires some normalization, right? I mean, you can always have like a matrix norm being the spectral norm times 10. I mean, that's another matrix norm.
Right, that's true.
So I think you want to maybe normalize that the identity is 1.
Yeah,
maybe that's going to work.
I think you're right. Let's say normalized. Yeah, there's definitely some notion where you can trade in any matrix norm, but yeah, of course you're right. They have to be normalized because you can just product by something and still get a norm.
Yeah. Also, maybe it's also just useful to point out that you can replace rows with columns and it will still be true.
Right. Yeah, and this should be obvious because when you transpose the matrix, right, it shouldn't change anything with respect to the spectral norm. Okay, so let's take a look at the proof of this. It's actually not particularly hard. So first, what we'll do is we'll fix an eigenvector or eigenfunction f with eigenvalue lambda. And what's our goal? Our goal is to prove, assuming this statement about the L1 norm of the rows, our goal is to prove that the absolute value of lambda is less than or equal to delta for any fixed eigenvector, and that'll prove the bound on the spectral norm.
I think you don't even need the absolute value, right? Just need lambda plus delta.
I mean, the spectral norm is two-sided. You do need it, right?
Usually it's one-sided, but yeah, it depends. You can define it either way.
Well, I mean, our way of defining random walk expansion is two-sided.
Sure,
So
no, I agree. That's the word.
we need it. In this case, we need a two-sided. Yeah, I mean, okay, sure, you can do it either way. In this case, we need it to be a two-sided bound, so I'm going to do the two-sided version.
Yeah, fair enough.
So in this case, let's fix tau in xk to maximize the absolute value of f. So to maximize f of tau. And then let's examine the following term, the absolute value of lambda times the absolute value of f of tau. And the idea here, I'm about to show you the calculation, but the idea here is that f is an eigenvector, right? So lambda f can equivalently be written as EF. And then you can use matrix multiplication to kind of turn this into a statement about the sum of absolute values over the rows, over a row of E. And this will end up giving the connection to this maximum that we have. So let's go ahead and actually see this. So this is equal to what? Lambda f applied to tau, but this is EF applied to tau because f is an eigenvector with eigenvalue lambda. And then just by definition of matrix multiplication, what is this? Well, this is the sum over tau prime in xk of E tau prime, f of tau prime. And then we can simplify things a little bit by using the triangle inequality. We can pull the absolute value inside. So this is less than or equal to the sum now of pulling this inside, E of tau prime, f of tau prime, or again, tau prime in xk. But remember that we picked tau to maximize the absolute value of f tau prime, right? So in particular, we can pull out the maximum, everything's positive, so we can pull out the maximum value here as f of tau. So we get that this is less than or equal to f of tau times this sum of tau prime in xk of E tau prime. But then this is just the L1 norm of the row associated to tau, right? This is the L1 norm of kind of E tau. And we're assuming that this is, by assumption, this is less than or equal to delta, right? So this is less than or equal to delta times f of tau. And now we started with absolute value of lambda times f of tau, right? So these cancel. And we just get that the absolute value of lambda is less than or equal to delta. So we get a two-sided bound on the spectral norm. Yeah, that's the whole thing. So it's just a little bit of manipulation, a connection between eigenvectors and the rows of a matrix. Okay, so maybe any questions so far on this claim or the transition probabilities that we wrote out? That we can bound the L1, the maximum L1 of rows rather than the spectral norm. If not, let's go ahead and use this to actually prove that the complete complex is a random walk expander. So in particular, it doesn't really matter which row you look at because in the complete complex, everything is symmetric and everything is uniform. So all the row sums will actually be the same. But we'll just look at some generic tau, I guess. So remember that E is kind of this error term, and we know exactly what the values of E tau prime are, right? So all we have to do is sum them up over a row to get our bound. So this is equal to the sum over tau prime of E tau prime. And looking back, so we computed this, or at least I claimed the computation and left it to you. But I claim that we have these values, and so all we have to do is most of them are 0. So all we have to do is care about the tau prime which are 1 away from tau, and the tau prime which are equal to tau. So let's write this out. So this is equal to what? Well, it's equal to let's do the tau prime equal to tau case first. This is equal to the number of tau prime such that tau prime is equal to tau. And unsurprisingly, there's only one of these, which is tau. The only tau prime equal to tau is tau. And then the value we got here was 1 over n minus k plus 1. So that deals with the first case. The second case is we have to sum across all of the tau prime which are kind of neighboring to tau. Right, so this is the number of tau prime such that tau prime intersect tau is equal to k minus 1. And then the value here that I claimed above is k times n minus k times n minus k plus 1. So to actually get a bound, all that's left is to compute the number of neighbors, right? What's the number of tau prime that are 1 away from tau? And I'm going to claim, and I'll leave formally proving this as an easy combinatorial exercise. I'll claim that this value, tau prime such that tau prime intersects tau, is equal to k minus 1. This is actually equal to k times n minus k. And okay, I'll tell you informally why this is. I'll leave the formal proof up to you. But the idea is to get to a neighbor of tau, to get from tau to some neighbor tau prime, what you can do is you start at tau, which is a k face, right? So this is some set of k vertices. You remove one of the vertices, and then you add in a new vertex, right? So when you remove one vertex, there are k choices for doing this. So kind of remove one, and we'll get to k minus 1 vertices. And then we'll add one back in. So kind of remove a vertex, and then we'll add a vertex. And we want to add a vertex to get to a neighbor. We want to add a vertex that wasn't initially in tau, and there are n minus k of these. Right? So this gets to tau prime in xk, that's neighboring. And so in this first step, there were k options. In the second step, there are n minus k options. And so you end up getting that there are k times n minus k total. And you can prove that there's a bijection between this process and neighbors, just because it always maps you to a neighbor. And for each neighbor, there's kind of an obvious way to map to it. So there are k times n minus k of these. And so if we plug this in here, right, this k times n minus k cancels with the k times n minus k in our value. And what we end up getting, kind of just skipping down here, is that this is equal to 1 over n minus k plus 1 plus 1 over n minus k plus 1 is equal to 2 over n minus k plus 1. And because we're in a d-dimensional complex, right, we only care about k being between 1 and d minus 1. So in particular, this implies that JND is a 2 over n minus d, actually slightly better, n minus d plus 2 or something like that, but close enough. A 2 over n minus d random walk expander. And in particular, for d reasonably less than n over 2, kind of as n goes to infinity, this in the limit, this approach is a perfect random walk expander, right? This approach is a 0 random walk expander. So as n goes to infinity, this approach is a 0 random walk expander. So in other words, as you take n growing to infinity, this is indeed essentially a perfect random walk expander. I mentioned earlier that kind of for finite complexes, it's not possible to have a perfect random walk expander, but this shows that in the limit, as you take n to infinity, you do indeed get this essentially perfect object, a 0 random walk expander. Okay, so that concludes our first example, that the complete complex is a 0 random walk expander. Sorry, is a nearly perfect random walk expander, 0 in the limit of large n. Okay, any questions on that before we move on? The next step is to show the relation between local spectral expansion and random walk expansion. Okay, if there are no questions, let's go ahead and move on. So this will be our last topic for the section, and then we'll move on. Shahar will give some applications to sampling algorithms, some really exciting recent breakthroughs in the last couple of years based upon all this machinery that we're building up. So we are gonna, we're going through a lot of machinery right now and structural theorems, but we are gonna see some cool algorithmic applications of this stuff. Probably next lecture, maybe at the end of this lecture, depending on how well this goes.
Well, probably not, since I haven't prepared for it.
Oh, well, I prepared it actually, so it's okay.
Cool.
If we, I don't think we'll get there, but if we do, I will start it.
I think worst case, we just finish a bit ahead of a bit earlier. It's fine. You can start like from scratch in this applications area.
Yeah.
Sure.
Well, I think we have just enough time to make it through to there, so it shouldn't
Go.
shouldn't matter. Okay, so let's go ahead and talk about the equivalence of these two notions of expansion, which essentially gives another way to think about random walk expansion. So the first thing I kind of want to note, and we've said this throughout, but this is a little bit, we're going to see that these are equal, more or less, up to some kind of factor in the dimension of the complex. And this is surprising because random walk expansion, is a purely global property. A priori, it has nothing to do with link structure, right? I mean, it turns out it does, but just looking at this is a property about kind of looking at levels of the complex, nothing local, and talking about, some equivalences between kind of moving up and down in the complex and moving down and up on the complex. And, somehow what this is going to show is this is very tightly controlled by the spectral expansion of graphs underlying links, which, to me is a surprising statement. So versus the local spectral expansion, mostly local. And so it's a little bit surprising that they're equivalent, but let's go ahead and see the theorem. This is due to Dickstein, Denur, Filmus, and Harsha. I think the paper is called Boolean Functions on High Dimensional Expanders. Really nice paper. I guess I should say the year. This is 2018, I think. Okay, so what's the theorem? So let x pi be a d-dimensional complex. Again, whenever I say complex, I always mean a pure weighted simplicial complex. I'll just say complex for simplicity. The following are true. The following equivalence between local spectral and random walk expanders hold. So first, if x pi is a gamma local spectral expander, this implies that x pi is a gamma random walk expander. So this is kind of the local to global side of the theorem. And this side is maybe actually slightly less surprising because we've already seen, this kind of thing before when we proved the trickling down theorem. And in fact, the proof won't be exactly the same, but it will be pretty similar. It'll be morally very similar to Oppenheim's theorem. And this will be our main focus for the rest of today. And then it turns out, surprisingly, the converse is actually true up to a constant factor. So in particular, if x pi is a gamma random walk expander, this implies that x pi is a 3 times d times gamma, so not quite a gamma local spectral expander, but off by basically the dimension of the complex, local spectral expander. So this is kind of the other way. This is global to local.
Actually,
right? We take it.
Do you know if in the second one, is it known if you need to lose this factor of d?
It's a good question, and I don't remember. I want to say the answer is, I know Yotam answered this question at some point. I can't remember. I think that the 3D is maybe not tight, but that there might have to be some, there might be some examples where there is a loss of D. Take it with a grain of salt. I'll check into it and tell people next lecture because it's a good question. Yeah, I'm not totally sure. So I guess it's worth noting that in cases it does actually matter whether this is tight in a sense. Like we'll see kind of in some sampling applications and things like that, a factor in the dimension of the complex actually, somewhat surprisingly ends up being really important. In particular, if gamma isn't that large, like if gamma is only 1 over d or something like that. Sorry, if gamma isn't that small, if gamma is only like 1 over d, then a d factor makes a huge difference, right? A d factor is then a trivial bound. It says nothing. So the difference, even though kind of I'm claiming this as a constant factor, in application, when the dimension of the complex isn't a constant, then this can actually be a really big gap. And yeah, I'm not sure if it's tight, but I'll try to look into that and mention it next lecture before the sampling applications. Okay, so we're going to focus on proving one for a couple of reasons. One is that we don't have enough lectures left to prove both of them. So we're only going to prove the first, which is kind of the same, keeping in the local to global paradigm that we've been going through so far in high dimensional expanders. The second reason is it turns out that kind of the first direction here is crucial to the sampling applications. And basically we'll see that a very slight modification of the proof kind of combined with some other observations is going to give us really efficient sampling algorithms. And Shahar will talk about that on Thursday. Okay, so let's go ahead and talk about kind of what, kind of an overview of what the proof looks like a little bit. In particular, it shouldn't really be anything surprising. It's going to be very similar to Oppenheim's theorem. So the proof will go through a variant of Garland's method. So the proof will use a variant of Garland's method. And remember that what is Garland's method? Garland's method was essentially a way of breaking up a function or whatever you're kind of interested in looking at over links in the complex, right? So we start with some kind of global object. We'll use Garland's method, which is really kind of just a buzzword at this point for some way of breaking down your object of interest over links of the complex. As far as I can tell, it really just means any way of doing this. So we'll use a variant of Garland's method, and we'll do kind of the same thing as with Oppenheim's theorem. We'll take a look at the Rayleigh quotient. We'll break it up into kind of more or less like Rayleigh quotients over links. We'll apply spectral expansion because we're guaranteed that each link, the graph underlying each link, is a spectral expander. And then we'll use Garland's method to lift it back up to the global object again, and this will give us the bound that we want. So we've seen this kind of structure already. It's how we proved Oppenheim's theorem. But the variant of Garland's method we're going to use is a little bit different. We kind of need to prove for this new application, we need to prove a new variant of Garland's method. And this is kind of a paradigm or a very common thing you'll see in the high dimensional expansion literature. We might get to in later lectures, I'm not quite sure, that there are kind of variants of this for variance, for entropy that are used in the sampling literature. I think there are different variants used in kind of agreement testing and error correction. Basically, what you want to, this whole paradigm is a kind of, you expect links to have nice behavior, like they're a local spectral expander, for instance. And so you take your global property and you prove some variant, some relevant variant of Garland's method, and then you just break it down, apply the property across links, and then use Garland's method again to lift it up to the global property. This is exactly what we'll do here. And I just want to highlight it before we go into it because it's such a common plan. It's such a common kind of proof overview strategy in high dimensional expansion. It's just used all over the place. You'll see it in, probably some of you will see it in your final project if you pick a high dimensional expansion related project. So I just kind of want to highlight it that this is what's going on in a lot of the related works to what we're discussing. Okay, so I need to tell you kind of what I've said a variant of Garland's method. It's similar to what we used in Oppenheim's theorem, but I should tell you what I actually mean. And in particular, what we're going to see is that we're going to have a variant of Garland's method that talks about a different way of breaking functions over links. So just as a reminder, when we proved Oppenheim's theorem, we used something called localization of functions to links. So what was localization? So the localization of a function f in ck to a link to x tau for some tau in, say, level xi, we wrote as the following. It was f tau and this was a function on the kth level of the link, right? So essentially we were lifting a function from the kth level of the complex up to the kth level of a link. And for all sigma in x tau of k, we defined f tau of sigma to be equal to f of sigma, right? So in essence, we were basically just kind of throwing out tau. This was what we called localization, and we used it to prove Oppenheim's theorem. We're going to look, in this case, the relevant notion of kind of breaking up our function is not going to be localization. It's going to be something called restriction, which actually I find a little bit more natural. So the restriction of f in ck to x tau for tau and xi will be similar, but essentially we won't throw out tau. We'll keep tau around. So instead of being a function on the kth level of the length of tau, it'll be a function, sorry, and we'll denote this as f bar tau, just to have some difference in notation between localization and restriction, since they're different notions of breaking up functions on the complex. So f bar tau, f restricted to tau, this is a function not on the kth level of x tau, but on the k minus ith level of x tau. And the reason for this is that we're going to keep tau. We're going to add tau back in of x tau, where for all sigma in x tau of k minus I, so this is a k minus I face in x tau, f tau of sigma is equal to f of tau union sigma, right? So in this case, it's really just a restriction. You're essentially restricting to the length of tau rather than a localization where we kind of throw out tau. So one way to view this, I'll try to maybe, the difference here is a little bit subtle. I'll try to maybe draw a diagram to make it a little bit more clear, So let's say this is level xi, this is level xk, this is level xk plus I. Let's call this tau. And then we have a function f on the level here. And let's say that kind of these are all the faces. So these are all the faces that kind of contain tau. So these contain tau. And then these also contain tau. So the idea is that, in essence, the restriction of f to tau is just looking at the function f across these k-level faces. They become, when you remove tau, they become a function on k minus I, the k minus ith level of the link, right? Because when you remove tau, you move down I dimensions because you're removing an I face. But in essence, the function still remains kind of on level k of the whole complex. In localization, it's a little bit different. You're actually, in essence, kind of lifting the function up to level k plus I. And then when you have like a k plus I face, sigma union tau here, right, the localization only looks at the value on sigma. Whereas the restriction down here, so here we also have maybe sigma union tau, but f bar of tau of sigma is equal to, it doesn't throw out tau, right? It's just equal to sigma union tau. So it's still kind of on a k face. So in a sense, localization kind of lifts you up the complex, whereas restriction just restricts to a face. It just looks at, okay, I'm going to look at this function only across the faces that contain tau. Okay, so this is a little bit subtle, the difference between these notions, but it's an important difference. So are there any questions between kind of the difference between localization and restriction? Or Shahar, I don't know if you have a better way to explain this. It's a little fiddly to explain.
Yeah, I mean, the things sort of look more or less the same when you just do it for like, far enough, but there are like subtle distinctions. Like, for example, so imagine you have a function on the vertices of a complex and you're doing, restriction, then sort of you go to a vertex, then you get a constant function, right? Sort of basically you move down. So the function stays on the same level globally. So when you look at a restriction, this is maybe the more natural thing to do. Sort of, you still have the function defined on the same level on the global complex, and just take it's the part of it that the link sees. While localization is sort of moving things up. So I mean, if I have a function on the vertices of a complex and I take a vertex, then I'm going to see a function of the vertices of the link. So it's a, I don't know, to me, the restriction might be more natural, but for some, but some applications may be local. I don't know. So the model is the same, but not quite technically the same. And some application need one and some need the other. So it's good that you see both.
Yeah. Yeah, I'm actually not sure if you can prove Oppenheim's theorem through restrictions. It would be interesting to try to figure out if you can.
Yeah, I try to do this. I don't know how to do it.
Right. Okay, so let's go ahead and see our kind of variant of Garland's method for restrictions. So I'll say kind of Garland's for restrictions. Okay, so let's kind of, we have the standard setup. So let x pi be a maybe a d-dimensional complex. So just like for Oppenheim's theorem, we're going to need to have some kind of statement about the adjacency matrix of the graph's underlying links. So let's define a notation for this, just like we did for Oppenheim's theorem. For all 0 less than k less than d, and let's say tau in xk minus 1, let a tau be the normal, weighted adjacency matrix of the graph underlying x tau. Then basically I claim the 3 following kind of local versus global equivalences hold. So I'll explain why we need these 3 in a second. It should be fairly obvious. So for all f and ck, the 3 following hold, and I'm going to move, I guess, to the next page here. So 2 of these should be familiar from when we proved Garland's method for localizations in Oppenheim's theorem. We'll have a way of breaking down just the squared 2 norm of f. So this will be equal to the expectation over tau drawn from pi k minus 1 of f restricted to tau, f restricted to tau. So it's the expected squared 2 norm over restrictions. The second is a relation, is a way to divide up kind of the quadratic form of mk plus. And this is similar with Oppenheim and how we were dividing up the adjacency matrix underlying the 0 link. So in particular, mk plus f, this turns out to be essentially the analog of, again, of what we saw in Oppenheim's theorem. This is tau drawn from pi k minus 1 again, of what? Well, this time a tau, f restricted to tau, f restricted to tau. So these are kind of analogs from the localization proof that we did. So these should be similar. And the third is something new, right? For random walk expansion, we're not only analyzing mk plus, we're also analyzing the lower walk, right? So we're also going to need kind of a Garland's method for the lower walk, for the quadratic form based on the lower walk. So this will be uk minus 1 dk f. And this is a slightly different form. It's still going to be kind of a local expectation over level k minus 1. So tau from pi k minus 1 of what? Well, actually, it'll be the expectation of f of tau squared over the length of tau. Or maybe I should write like pi tau 1. So all of these inner products are over the links, right? Just like when we did Oppenheim's theorem. So this one is new. We didn't need this for the trickling down lemma, but actually it's probably the easiest of the 3 to prove. We'll see later. So what I want to do now, the proof of this is fairly technical. I mean, it's nothing too dissimilar from what we've seen before. It's going to be kind of doing this whole conditional game between moving of levels, k and k minus 1 in the complex. And kind of we saw an explicit version, before we started working with the joint distribution, we saw kind of a written way through to do this when we proved Garland's method before. Now we're going to see kind of how to do it from the joint distribution perspective. But it's a little bit technical. And so kind of before proving this, I actually just want to go ahead and prove the local spectral expansion implies random walk expansion result, assuming this lemma, because it's pretty easy. It's basically the same kind of argument as we've used to prove Oppenheim's theorem.
Max, maybe just before you do that, Yeah, I just want to say one thing. So one thing that happens with restrictions that didn't happen with localization is that it sort of helps simplify the expressions. In what sense? So remember that, for when we proved the Oppenheim theorem, we were lucky that it was actually just enough to prove it for d equal to 3. So for three-dimensional complexes, so it was of everything that didn't grow too much. But here we have a general k. So you have a function f on k faces. And this might be complicated combinatorially. But if you think about the right-hand side, that's in number 1 here, then what do you have? You have an expectation of a k-1 faces. Another restriction is just a function of vertices. So now you have a graph, and you have a function on the vertex of this graph. So this has all become a question about graphs. So basically what restriction allows us to do is to move from questions about high-dimensional complexes to basically questions about graphs, which localization didn't allow us to do. That's it.
Right. Or it only allowed us to do it because we were in d equals 3 specifically.
Well, there we just started with f being a function of the vertices to begin with.
Right. And then lifting up one level, you ended up with a graph because you were at d equals 3. Right. But in this case, there's no kind of, at least as far as we know, there's no kind of simple induction to only simplify to the d equals 3 case. And so you need this kind of more general way of reducing to graphs. Okay. So let's go ahead and prove the result. So proof that local spectral expansion implies random walk expansion, assuming lemma. Okay. So the proof is surprisingly easy. So let's recall what the goal is. We want to prove that the spectral norm of mk plus minus the lower walk minus uk minus 1 dk is less than or equal to gamma. And how are we going to do this? Well, now we're going to go back to our tried and true strategy, right? Now we're going to bound the Rayleigh quotient. So by variational characterization of eigenvalues, we've seen kind of over and over again, it is equivalent to show that for all f in ck, the absolute value of the Rayleigh quotient is bounded, right? In particular, the following holds: mk plus minus uk minus 1 dk, f is less than or equal to gamma ff. So I've multiplied through by the norm of f already, but if you just divide by it, this gives you the absolute value of the Rayleigh quotient. That's all we're doing. And the way that we're going to do this is, exactly what we did with Oppenheim's theorem. We're going to use Garland's method to decompose the left-hand side. We're going to apply the spectral expansion of links, and then we're again going to use Garland's method to lift it back up to the global property. This is only a couple lines, so let's go ahead and just do it. Okay, so first of all, let's simplify this a little bit by using bilinearity of the inner product. Let's just separate mk plus and the lower walk, right? So in particular, the left-hand side can be written as mk plus f minus the lower walk. For simplicity, I'm maybe going to drop the indices here. They should be clear from context. Now we're going to apply properties 2 and 3 in the lemma above, right? So remember, we know exactly how to break down both of these terms locally, and then we get these objects over graphs. So let's go ahead and do that. So this is equal to the expectation over k minus 1 faces. So tau from pi k minus 1 of what? Well, on the left, we have a tau, f restricted to tau, f restricted to tau. And then the right-hand term is also this expectation over k minus 1 faces, right? So with bilinearity of expectation, we can just join them into the same expectation. So then this is minus, what was this one? Well, this one was the expectation over f of tau squared, right? So we have the absolute value of this term. And then let's simplify this a little bit, again, by using the triangle inequality. Let's pull the absolute value inside. What we're going to get is the expectation of tau over pi k minus 1 of the absolute value of a tau, f restricted to tau, f restricted to tau, minus the expectation of f of tau squared. So now we have a statement over graphs, right? Each of these individual statements is some kind of statement about the graph underlying the length of f restricted to kind of the graph underlying the length of tau. And notably, we know that a tau is a two-sided gamma spectral expander, right, by assumption. And I claim that this tells us the following useful fact, which I will explain, but not, I'll leave the formal proof to you. I claim that a tau, f tau minus expectation of f restricted to tau squared is less than or equal to gamma times the squared 2 norm of f restricted to tau. And we maybe haven't seen quite this form of using spectral expansion, but we have seen very similar things to this, and it's a standard trick for using regular expanders. So kind of maybe morally, why is this true? Well, the idea is that this right-hand term is basically the trivial eigenvector, like the portion of this left-hand side that is the projection on the trivial eigenvector. So remember that the kind of top eigenvector here, so the idea of the proof is something we saw kind of when we proved the variational characterization of eigenvalues. We've seen, I think, kind of a few times throughout the course. We want to kind of decompose this side by its eigendecomposition. And the idea is that the first eigenvalue that has eigenvalue 1 is the constant function. And so if you work out kind of the projection of the constant function, this ends up giving you this squared term. So essentially the projection onto the constant function, the trivial part, exactly cancels with this lower walk portion. It exactly gives you the constant term. And you should be able to, it's a simple computation. I suggest going through this because we know that the kind of the eigenfunction corresponding to 1 is just the constant function, and so you can compute kind of its projection. And then all of the remaining eigenvalues are bounded by gamma, right? And so all of the remaining weight gets hit by this gamma term, and so what you end up with is kind of the total norm of the function, and then bounded by gamma, because all the other eigenvalues are less than or equal to gamma. So that's kind of the sketch of the proof of what's going on here. Formally, I'll leave it as a basic exercise with to do with expanders. But once we have this, we're essentially done, right? Because we can now, if we continue this equation, if we plug in this claim, what do we get? Well, we get that this is less than or equal to gamma times the expectation of tau drawn from pi k minus 1 of f restricted to tau, f restricted to tau. And then now we can apply the first property of Garland's method, right? This is exactly equal to gamma ff. And that's what we were trying to prove. That bounds the absolute value of the Rayleigh quotient. It's probably worth noting, and this is kind of a sneak peek, that you could actually do slightly better than this. So slight improvement is possible. And this is actually very similar to when you improved kind of the hitting set bound on the homework, where you kind of had to break things up into parallel and perpendicular parts, and then you ended up getting kind of a slightly better bound with like 1 minus beta or 1 minus gamma or something like that. And this turns out to be really important for sampling applications. And Shahar will talk about this in the coming week. This kind of slight improvements will give very impressive sampling applications, which is pretty cool. So basically, it will be this almost exactly the same proof, slightly modified, slightly improved. Will give a really cool result. So stay tuned for that in the coming week. Okay, any questions about this proof? Basically, we've shown, as soon as you have Garland's method, really all it is you analyze the Rayleigh quotient by breaking it down by Garland's method. You apply a standard spectral technique for two-sided spectral expanders, and then you just lift it using Garland's method back up to a statement about the global function f, and that's all it is. So the heavy lifting here is really coming from Garland's method. Okay, so if there are no questions, let's spend the last 10 minutes proving Garland's lemma, or maybe I shouldn't call it Garland's lemma. It's a variant of Garland's method. We probably don't have time to prove the whole thing. I'll prove the first two statements, and then maybe we'll just leave the last one in the notes because it's technical but kind of similar in flavor. Or I can finish it Thursday, whatever people prefer, I guess. So let's go ahead and see how to prove two of the three statements. I think we can get through. Okay, so let's take a look at the first. So remember, the first statement is that FF, the inner product of F with itself, is equal to the expected inner product over K minus 1 faces of what? Of the inner product of F restricted to tau with itself. Okay, so this is the first statement, and we saw a very similar, we already proved a very similar statement of this in the localization variant, but let's see how it works for restrictions. Slightly different, I guess. So let's start out by expanding FF. So this is equal to what? By definition, this is the inner product over pi k, over tau drawn from pi k. Maybe I'll write sigma drawn from pi k of f of sigma squared. All right, this is just the definition of the inner product. And then we'll do kind of what, our general strategy when we were working with kind of adjointness, and when we were working between, we want to kind of move to k minus 1 and talk about k minus 1 faces versus k faces. Often when we do this, it's useful to move to the joint distribution, right? So instead, we'll write this as an expectation over the joint distribution. So remember, this is over kind of chains of faces, where you pick sigma d from pi d, and then you pick the remaining ones by removing a vertex uniformly at random. It's a very simple process. And so this will be equal to the expectation over f of sigma k, the kth element of this chain, squared. And the key here is that we can kind of now marginalize over k minus 1, right? We can look at this expectation kind of given that sigma k minus 1 has a certain value. So in other words, we can write this expectation as actually a sum over k minus 1 faces. So a sum over tau and x k minus 1 of kind of the probability that sigma k minus 1 is equal to tau times the expectation, given the fact that sigma k minus 1 is equal to tau, right? We can always marginalize, in an expectation, we can always marginalize over the joint distribution and then kind of look at the conditional value. This is always equivalent, right? So then we have the expectation of f of sigma k squared, given that sigma k minus 1 is equal to tau. So this is the same kind of conditional, trickery we were doing when we proved that the up and down operators were adjoint. It's just a useful way to write out the expectation when we want to kind of talk about level k minus 1. Okay, so the first thing to notice is that the probability that sigma k minus 1 equals tau is just the marginal, right? So this is just pi k minus 1 of tau. So particularly, we can write this as the expectation over tau from pi k minus 1 of what? Of the expectation of f of sigma k squared, given that sigma k minus 1 is equal to tau. And so now we want to analyze this inner expectation. And what we'll look at is we'll ask kind of how is sigma k distributed given sigma k minus 1 is equal to tau. Well, we've seen this before, right? Sigma k will be equal to tau union v, where v is drawn from the link of tau, where v is drawn from pi tau 1, right? This is just by definition of how we define the joint distribution pi. When we look down, we remove things uniformly at random. When we look up, we essentially end up using the kind of conditional distribution over links, right? So sigma, given sigma k minus 1 is equal to tau, when we draw a k face, all we do is we draw a new vertex v from the distribution over the length of tau, right? So we draw v from pi tau minus 1. What does that mean? Well, that means we can rewrite this as follows. This is equal to the expectation over tau drawn from pi k minus 1 of the expectation of v drawn from the link pi tau 1 of what? Well, f of tau union v squared. But f of tau union v we can rewrite, right? This is by definition equivalent to f restricted to tau of v. And then this inner expectation, by definition, this is the inner product of f tau with itself over the length, right? Over x tau of 1. And so we're done. This is exactly what we were trying to prove. Okay, so kind of morally, what have we done here? We just said, okay, well, we can write things out in terms of the joint distribution, and then we can always marginalize across kind of any level of the complex, and then look at the conditional distribution at level k given that marginalization. And because we want to look at kind of the expectation over k-1 bases, the natural choice is to marginalize over level k-1, and then look at how the expectation then, how the conditional expectation looks given this choice of sigma k-1. And we've shown that in fact it looks exactly like the inner product of f restricted to tau with itself. And kind of that's the trick here. Okay, so let me prove. Actually, I will prove the third. I don't think we have time maybe to go through the second one. It's a little bit longer, but I'll now prove the third statement, which is the quadratic form of the lower walk. Actually, I realized maybe I said this was the second statement. No, it's the third. Yeah, so we'll prove this third statement now. So the third statement is that uk-1 dkf, f is equal to what? It's equal to the expectation of tau over pi k-1 of the expectation of f restricted to tau squared. And this one will actually be a little bit easier, only because we've kind of actually already done the hard work on this one. In particular, it's basically going to follow from the adjointness of u and d. Right, so in particular, we have that the left-hand side is actually equal to, because u and d are adjoints, this is equal to dkf, right? And let's just expand this out. This is equal to the sum. So this is dkf, remember, is a function over k-1 bases. So this one, we basically don't have to do any kind of conditional trick, or well, we will when we fill in the definition of the down operator. But the point is we're already in a sum over level k-1, right? So we can just write this out. This is tau in x k-1 of what? Of pi k-1 tau times dk of f tau squared. So let's now take a look at dk of f tau. What is this? Well, by definition of the down operator, this is the expectation of f of sigma k, given that sigma k-1 is equal to tau. But we just talked about how sigma k is distributed here, right? We can equivalently write this as sigma k is equal to tau union v, where v is drawn from the length, right? So this is equivalent. This is over the joint distribution. And this is equivalent to what? The expectation over the length, v drawn from kind of pi tau 1 of f of tau union v, which is equal to, right, f restricted to tau of v. So this is just dkf of tau. So plugging this back in, kind of plugging this back into what we had above, what does this get us? We get the sum over tau in x k-1 of pi k-1 tau. And then we get this expectation over the length of f restricted to tau squared. I guess I don't need this v in here. F restricted to tau squared. But this is just the definition of what we want, right? This is just the inner product. Oh, sorry, not the inner product. This is just the expectation, right? We have a sum over pi k-1 tau. By definition, this is the expectation over tau and pi k-1 of what? Well, of this squared term, right? Of the expectation of f restricted to tau squared. Okay, so this one actually is pretty similar to the above, right? We're still just using this trick that the conditional expectation of a k face based upon a k-1 face is exactly drawing one vertex from the length of that k-1 face. right? In both of these cases, that's how we've moved between levels k and k minus 1. In this case, we additionally use the adjointness of D and U to our advantage to make things a little bit simpler. But that was kind of the essence of both proofs, is that you marginalize over level k minus 1, and then the conditional distribution moving from k minus 1 to k is just by adding a vertex in the link. And this lets us move between a statement over level k and an expectation over k minus 1, and then some statement about the graph, vertices over the link, the graph over the link. Okay, so we don't have time to work through the third one. It's similar in form, it's in the notes. I don't know if we want to cover it on Thursday or not. I guess, I don't know, I guess Shahar and I can decide, or we can put up a poll or something on whether people want to see it. But it's basically just more of the same. It's a slightly more complicated version of this because MK plus is a bit more complicated of an operator than the lower walk. But it's the same style idea. You just, condition between levels of the joint distribution and use this to move over links from the global perspective.
Yeah, I'm not sure there's going to be much value in going through it in class. I mean, I think it's probably better if people just read on their own. We have it in full detail in the notes, so you can just read on your own. And if there are any questions, we can answer. But it's probably easier if you read on your own.
Yeah, I agree. So I mean, you should be kind of equipped to understand it, knowing these proofs, because it's basically just a slightly more complicated version, like I was saying, of exactly the same thing. It's always just kind of marginalizing over the level that you want to have an expectation over, and then kind of fiddling with the functions until they give you what you want. Yeah, okay, so we're out of time, but I'll stick around to answer any questions that there are.
Yeah, maybe let's just make a couple of comments. First, just a logistic comment. So this Friday, I need to postpone my office hours to 1 to 2 p.m. So I'll post that on Piazza. The other one is that, so basically, like Max said, so what we've done so far is prepares all the machinery we need so that we can actually apply to some interesting problems that come in CS. And what we're going to do for the remainder of the quarter probably is go through some of these applications. In particular, many of these applications are very recent, from the last maybe 3 or 4 years. And the theory is still being developed, but there are already some really cool ideas that we can teach you. And basically using various techniques to analyze mixing of Markov chains that come in applications and use them to build sampling algorithms. And we'll start with simpler techniques, and then we sort of build our way towards more advanced techniques that can apply to a wider range of problems, or could be, give better parameters and so on. And then we're still not sure how much we're going to cover. We're still, Max and I are going to discuss this later today to see exactly how much we're going to cover. But again, just be aware. I mean, even if we cover everything that exists today, like in a couple of months, there will be new results. So if you're interested in this area, then I mean, just be aware it's a very active area, which is really exciting, and people are keep finding, first of all, new applications, but also ways of simplifying and unifying the existing applications using this machinery.
So for context, for instance, I think in the last month, there were 3 new papers all on the same sampling idea.
Yeah. And the papers were not identical, so each one had new ideas.
Yeah, they were, yeah.
So, yeah. Yeah, and probably we will not have time this quarter to touch on topological aspects of high-dimensional expanders, just because we need to choose something. But we could discuss. But if there's interest, I mean, we could decide maybe sometime next year to have like another course or reading seminar or something. People who are interested in topological aspects of HDX. But yeah, we'll see about that.
I guess a final logistical comment, which is that I do not have office hours after this since I had them on Sunday instead. So just as a reminder. Okay, let's, I guess I should stop the recording. How do I do